This research paper introduces the concept of weakly constrained double field theory, DFT, to quartic order, a promising approach to quantum gravity. DFT is a subset of closed string field theory on a toroidal background, encoding massless fields and their massive Kaluza-Klein and winding modes. The theory is subject to the weak constraint, originating from the level matching constraint, which makes it challenging to extend the construction beyond cubic order. Hull and Zwiebach initially constructed DFT to cubic order in 2009, but it remained an open problem to extend this to quartic and higher orders. The authors of this paper use the framework of homotopy algebras to obtain DFT as a double copy of the kinematic homotopy algebra of Yang-Mills theory. The paper begins by reviewing the motivation for DFT, which aims to find a renormalizable or UV finite theory for the gravitational field, including massive modes, that recovers general relativity at low energies. DFT is a promising subsector of string theory that inherits some of its unique characteristics, such as dualities and new effects governed by the parameter alpha. The authors then outline their construction of weakly constrained DFT to quartic order, which uses two ingredients: the double copy from scattering amplitudes and the homotopy algebra formulation of field theory. They start from Yang-Mills theory, viewed as a homotopy Lie or L-infinity algebra, and strip off color, leading to a kinematic algebra K that is commutative and associative, up to homotopy. The authors find a structure close to an L-infinity algebra, but it is obstructed due to the flat space wave operator being of second order. They formalize these square failures and define a more general algebraic structure. For the double copy of Yang-Mills theory, they introduce a second copy K of the kinematic algebra and seek the L-infinity algebra of gravity on Kk. The authors impose the constraint increment equals 0, thereby gluing together the two factors by identifying coordinates x with coordinates x, and construct the L-infinity algebra and hence weakly constrained DFT to quartic order. This construction not only solves a major problem in double field theory but also opens up new research avenues for deriving color kinematics duality and double copy from first principles. The paper then delves into the details of the L-infinity algebra of Yang-Mills theory, explaining how the gauge algebra, nonlinear interactions, and so on are described by multilinear brackets Bn. The authors display the structure of the L-infinity algebra for Yang-Mills theory, including the action written in terms of auxiliary fields, and the graded vector space K, which encodes the color-stripped local functions on spacetime. The paper discusses the construction of a new kinematic algebra for weakly constrained double field theory, DFT, using the BV square infinity algebra. It begins by defining a C-infinity algebra on the vector space K, which is a space of gauge invariant functions, with a nilpotent derivation M1 and a two-product M2. The C-infinity algebra is part of a larger BV square infinity algebra, which includes a B operator, a two-bracket B2, and a three-product M3H. The BV square infinity algebra has square deformations that act on K, and it is expected to have infinitely many higher products. The paper then introduces a new kinematic algebra on the tensor product x equals k circled times k, with a nilpotent derivation M1, a two-product M2, and a three-product M3H. This C-infinity algebra is also part of a larger BV increment infinity algebra, which includes a B- operator, a two-bracket B2, and a three-product B3. The BV increment infinity algebra has increment deformations that act on X, and it is expected to have infinitely many higher products. The paper explains that the algebraic structure of X can be transported to the DFT subspace VDFT using homotopy transfer. This involves defining a projector P increment onto Kerr increment, which is a map from a larger space to a smaller space that obeys the homotopy relation. For the special case of a doubled Euclidean torus background geometry, the projector is explicitly defined in terms of Fourier modes. The paper concludes by stating that the kinematic algebra on VDFT is part of a larger BV increment infinity algebra, which will be the starting point for constructing weakly constrained DFT at quartic order. In the context of double field theory, DFT, the authors aim to construct a gauge algebra for weakly constrained DFT on a torus. They start by introducing a homotopy map H, which is a degree 1 operator obeying B1 H equals 1p increment. The homotopy transferred maps, denoted with an overline, are computed systematically once the homotopy map is given. The gauge algebra is encoded in the homotopy-Jacobi relation, which takes values in the space of gauge parameters and has 3 components. The authors work out the component corresponding to lambda micro, and find that the non-locality inherent in 1 increment plus is unavoidable, as there is no overall increment plus that can be factored out to cancel it. This changes after replacing the field in the expression for B3 with B1, lambda, where the non-locality can be removed using the weak constraint and the projector P increment. The paper discusses the development of a weakly constrained double field theory to quartic order, with all dimensions toroidal and doubled. This theory is based on homotopy transfer and ejective field theory, which allows for the construction of a gauge-invariant double copy of Yang-Mills theory. The key result is the emergence of a homotopy-Jacobi identity, derived from the kinematic algebra of Yang-Mills theory. This identity is crucial for understanding the gauge structure of double field theory, which follows from Yang-Mills theory. The authors also explore the connection between double field theory and color kinematics duality, demonstrating how this duality can be applied to derive the quartic action of double field theory. They use L-infinity algebras to describe the kinematic algebra of Yang-Mills theory, and apply this framework to derive the gauge structure of double field theory. This work extends previous studies on the subject and provides new insights into the relationship between double field theory and color kinematics duality. Furthermore, the paper discusses the outlook for future research, including generalizing the double field theory to Lorentzian backgrounds and cosmological backgrounds. It also highlights the importance of understanding the kinematic algebra of Yang-Mills theory to all orders, as well as extending the double field theory to exceptional field theory and genuine in-theory modes. In conclusion, the paper presents a significant advancement in the development of double field theory, providing a gauge-invariant double copy of Yang-Mills theory through the use of homotopy transfer and kinematic algebra. The work opens up new avenues for further research, including generalizations to different backgrounds and extensions to other areas of theoretical physics.